Good morning, everybody. So, last class we've seen about the single cycle data path for load word, store word, and branch on equivalent. So, quickly going through the single cycle data path. So, we have uh, both the data and the control signal for the particular instruction is being generated in the same cycle. So, that was the concept here. So, as you see, the fetching the instruction in the first phase. So you have next reading the source from the operand from the register. So here you have the operands, the source operands being read using in the register file. Now you perform the extend sign immediate operation. So and you load the base address of the offset. So with that you load the compute the base address from the with the offset, and so you arrive at the what is the address location that you have to write in the data memory. So load the data from the memory and then you write it back to your register file. So register file. So apart from this, you have one more step, which is you are incrementing the program counter. So in order to point to the next instruction. So now we will see, in contrast, we will see how this multi-cycle architecture is going to be. So when you look at this, so the instruction processing cycle is divided into number of states. Okay, so a stage in the instruction processing cycle can take multiple states. So say for instance, each state will take particular cycle. So multi-cycle microarchitecture sequences from state to state process in the instruction. So there we are processing from cycle to cycle. So now in the case here it is one state is state. State it is completely determined by the control signal in that state. Okay, so now you have the data and the control signals for that matter. So now the behavior of the machine in the state is completely determined by the control signal in that state. So the behavior of the entire processor is being fully specified as the finite state machine. Since so is defined or is otherwise the finite machine, finite state machine architecture. So your FSM architecture, because it is the instruction processing cycle are divided into number of states. So in a state, two things happens. We've already seen the two entities. So in a state, the control signal control two things. One is how the data should process the data, and it is going to generate the control signals for the next clock cycle. So that is going to happen in the multi-cycle microarchitecture. So we'll typically example of load word LW operation. So again here your first step in execution of the load word operation is with help of your state elements, which is a unified instruction and data memory being associated here. So first instruction, the first state is going to have what happen is that fetching the instruction. So it is now very similar to that, but then you have the control signals generated for the next operations. Next operation is read the source operands from the register file. So for us, for that the corresponding controls are determined in the current state itself. So now the next operation is going to be reading the source operand from the register file. So this is the reading the operands from the register file is taking place. So based on the instruction that has been decoded. So next is sign extend immediate. So the sign extend immediate is going to perform when you are, since load word is an again is an immediate type of instruction, you have the sign immediate operation to be performed. So you assign extend the immediate value. So now you add the base address to the address offset. So now you have addition operation, that is your sign int of the register value is happening, and the ALU is being operated. Use it here in case of this going with the signed immediate value of the register data. So now upon the ALU result is being out. So next clock cycle, what happens is that your load data from the memory and it has to writes back to the register file. So that is the operation pending. Now it is going to generate the address offset, and now the data is being loaded to the before it is loaded, the address is being generated here. So in the next case, you can see is your target address being arrived, and you have the control signal available for register write here. So next step will be register writing. So your in your register data set has been this is the next operation. You have some addition operation over here, and before that the program counter value is upgraded. So we're incrementing your program counter. So now this is the multi-cycle operation data path. So when you consider the difference, so this is again very similar to that of your multi-cycle, but only thing is this: the next instance control word is being control signal is being determined in the previous state itself. So that is the path of the next instruction will be carried out in one state. So typically, when you understand this, so similarly, we have looked for the R-type instruction and the branching or your this jump instruction as well. So this is a complete multi-cycle process. The complete microstructure. Initially, you had okay. So when you initially saw your when you look into your control unit, what we had was a main decoder, and we had the option memory to register operation. Then you have memory write control signals. Then your branch. Then you have the ALU SRC and your. So this was the options with the main decoder of your 5-bit opcode. Next, you have the functional code also with respect to R type of instruction. Your ALU decoder had ALU controls. So here you can see what is the difference with respect to your how it is going to contrast with your multi-cycle your multi-cycle is that you have register enables here. So you have the signals with the register enables. So this register enable allows you, so you have the multiplexer which is going to select the main controller of using that 5 output. So there is a multiplexer option here. You have, apart from that, on your single cycle processor, you have something like your IR write, your instruction register write, memory write, your PC write, your branch and read write. So all of the extra main controller with respect to your FSM. That is your multi-cycle processor, and you have similarly you have the function codes which is related to the ALU decoder also. So this is the complete multi-cycle processor which would look like when you're pairing with your single cycle processor. So next so this is the important point that we have to understand here. So when you're looking into this picture, you will understand what is the so now this is with respect to your comparing your high level idea of your FSM processor with that of your single cycle machines. So as you have already we have the basic 6 operations, that is fetch instruction, decode instruction, read registers, register arithmetic. Then you have your read memory operation, write memory operation, write your registers and update your program counters. This is the basic fundamental stages of. So, but it differs with type of the instruction that you're using with. Say similarly, if you are working on a single cycle, so it is going to take all the instruction, complete instruction to happen will okay. So now the complete instruction execution is going to take place in single cycle. So that is, it is called as single cycle microarchitecture. So you have different cycles. So you can see the maximum cycle, or the cycle time is determined by the slowest instruction. So here, if you see, you have the time limit over here, which is empty. The process is free, idle in this case. So idle during this period. So in your execution of your jump on arithmetic left, you have a time period of your cycle, which is your process, where your process is going to be idle. So your slowest instruction is going to determine the cycle time in case of your single cycle process or a single cycle architecture, microarchitecture. So though you have got not all the operations or the all the stages of your instruction sequence is not happening in on all your executing the instructions. Say for particular, you don't have a few instructions like your register arithmetic or read memory. So such instructions are missing out in your jump instructions. So your slowest instruction is going to determine your cycle time. So this is one cycle, and this is going to be followed for all the instruction execution. So the slowest instruction of that is going to determine the cycle time. So now each instruction, you have to again remember that your each instruction executed in one cycle only. Okay, so your load word is executed in one cycle, and your add is executed in the next cycle, and your jump instruction is executed in the next cycle. So you can see a lot of time slot has been available where your processor remains idle. So when you compare that to your FSM processor, your finite state machine, so what happens is you see that your instruction execution of each instruction execution is divided into multiple cycles for that matter. So each cycle you're going to have one state being executed. So you have the fetch, decode, evaluating the address, fetch operation, execute, and store operation. So now all this is going to happen. These are going to be the states. So your one clock cycle is determined by your state, the complete state of. So this is how it is going to differentiate. In FSM data part requires thinking about required FSM states for executing that particular instruction. So if you see here, the instruction is divided into multiple states. Multiple cycles for that matter. So your one cycle, one clock cycle is going to do execute one state. So now here the advantage is that your the slowest stage, so which is going to be the slowest stage. So now that is going to determine your cycle time. So this is the difference when you compare it against your single cycle machine is going to operate with. So this is the case when you are talking about your implementing your multi-cycle and that is your FSM machine, and your in case here your single cycle machine. So when you compare it, it is going to look like this. In terms of, this is the timing diagram that we draw across in order to get a clarity of things. So now if your typing diagram is going to help you out in understanding the advantages of your implementing your ISA architecture. So next thing is that you have the further you have come up with the so we'll further our modern days computers will come up with advanced microarchitecture, that is your pipelining architecture. So to get introduced, so first why should we go for this? You should understand now what is memory access latency first. So here the increased frequency is the number of cycle it takes to access from your memory, main memory for that matter. So when you go for something like your deeper pipelining concept, so this is going to increase the frequency, and there is going to be certain types of disadvantages when you are going to work on your pipelining architecture. So first, before that, we'll understand. We'll understand what is a kind of pipelining concept in microarchitecture. So we have already got into a glimpse into it. So moreover, now let's understand this in a different way now. So in the microcoded machine, what happens is that some resources are idle in different stages of the instruction process. So say for instance, if you're working, fetch logic is idle when your add is being decoded or executed. Yes, so your fetching is only accessing your memory. So but adding operation is performed in your ALU. So sometimes your ALU is free, or sometimes your fetching or your wires which is related to fetch the instructions are free in some in execution of different stages of instruction processing. So now if you are able to club up the processes and use the resources to be most of the time, then you have to go with the concept of pipelining. So pipelining is that that ideology where you use idle resources to process other instruction. When I'm doing some fetching operation, so something is where memory read and write is only involved with. Now I can perform the ALU operation which is being carried out in my arithmetic and logic unit. So I'm trying to use the idle resources to process the other instruction when something else is processing. So now each stage processes a different instruction. So that we have to understand. So when you decode the AND operation, we are trying to fetch the next instruction. So that we have already seen with an analogy to a laundry application in our previous classes. So it was when one fellow is drying the clothes, the other is utilizing the availability of the washing machine to wash his clothes. So now this is the optimal or complete usage of your resources is taking place. So this is like picking an assembly line. So if you look into an assembly line like your bottle filling application or any automation industry, or some manufacturing industry. So it is like assembly line, everything will go in the line. So all the time, one operation is not idle in processing one product. So when one product is in the advanced stage of the manufacturing process, you have the X product in the other stage of the manufacturing process. So in an assembly line, you can think of. So now, if you understand the advantages and the disadvantages with respect to your pipeline architecture and multi-cycle machines, so you have the advantages like it is going to improve the instruction throughput by reducing your cycle per instruction. So that is one advantage with respect to your pipeline architecture. And another disadvantage that we are looking at, it needs more logic, and higher power consumption is one bottleneck with respect to your pipelining architecture. So now let's understand the execution of 4 independent acts. Before we get into the pipelining concept with respect to your single cycle processor and your pipeline architecture, we'll understand something like your execution of 4 independent add operation. If I'm trying to perform, what happens? So now here, let me consider this. I'm performing so add operation. So for that operation, I need fetch, decode, execute, write. Say these are the 4 basic operations sequences that I have to follow. So in the multi-cycle, if I'm trying to distinguish my multi-cycle with from that your pipeline architecture, so here I will have in multi-cycle operation, so I will have one the complete instruction being executed, and then only the next instruction is going to start with. So this I'm considering each state. Okay, each state. So the entire so one instruction to execute is going to take place, in this case, 4 states. So after this 4 states or 4 cycles are being completed, then it takes up the operation of addition of the next adding operation, addition operation. So this is the operation that is being performed, operation across your time scale. So, and if you contrast with your pipelined architecture, now you have, you can see what is the time consumed to perform this 4 independent adding operation with. So you can see here, when the first instruction is fetched, and now it has moved on to your decoding stage. Now I have my second AND operation taking up your fetching phase. So similarly, when my second operation is decoding, now my third instruction is going into the third AND operation is going for the fetching phase. So this is how it is going to happen. Again, it is split up. Each of instruction is split up into states. But see how parallelly, or this is the pipelined architecture. So the time consumption of executing 4 independent AND operation are drastically. This is the contrasting between your execution through your multi-cycle operation and your execution via your pipelined architecture. So, but then this is fine if I'm working on an independent operations. So, but the issues that we'll face using in your pipelining architecture is that one is the data dependency. So, though we are now working on independent AND operations, so there we don't see any data dependency. So, but if you are working on some data dependency task, then you will have a stalling problem. Pipelining remains remains high. So how we are going to classify this data dependency types and how you are going to sort it out, all are going to be important things that you have to address. So this is the pipeline architecture overview, and what is the data related dependencies issues that we'll face, and what is the stall concept, how it is going to your one is going to cause stall in this pipeline architecture. That okay, if no doubts, thank you. We'll understand about the problems that we are facing, what are the hazards which is related to each architecture.